So welcome to today's lesson, and we're going to look at A2 electrochemistry. So the last time that you probably looked at electrochemistry was IGCSE, but A2 electrochemistry looks at a whole wider range of electrochemistry that you probably haven't visited yet. So first I want to start off with this relationship, F equals LE. So again, this probably is the first time that you see this equation. What F stands for is Faraday's constant. L is Avogadro's constant, which is probably very familiar by now to you. Number or constant, same thing, which is 6.022 times 10 to the 23. And I'm sure you've seen this number before. This is the number of atoms in 1 mole. And E is the charge on 1 electron. And if you study physics, then you're also familiar with this. It's 1.66 times 10 to the minus 19. So we have this equation. Now, what does this even mean? So Faraday's constant is the charge on 1 mole of electrons. And as you can see, this makes sense because we have Avogadro's number included in the equation, and we have the charge in 1 electron included in the equation. So looking at that, we multiply these two, we should say that the Faraday's constant is just the charge in 1 mole of electrons. So this number comes out to be 96500 coulombs. And if you know from physics, the standard unit for charge is coulomb. So we say C for coulombs. Now, where do we even use this? Well, there's a very important relationship that you need to know. Charge is proportional to mass deposited. And what mass deposited are we talking about? Let me just highlight this. Well, if you look at this very standard example of electrochemistry, if you have 2 electrodes, 2 copper electrodes, this being the copper. So since the ion of copper is Cu2+, copper needs to take 2 electrons from the battery. When these 2 electrons go into the copper cathode from the battery, the copper ion is discharged and the cathode's mass increases. So 2 electrons are taken away, the copper ion is discharged, so the mass of cathode increases. And you probably know this will have copper, pure copper around it, and this will shrivel down with the impure anode will shrivel down, and all the impurities will fall down here. And you also know this from IGCSE. This is called the purification process, using pure copper and impure copper. So connecting this concept that you learned in IGCSE to this rule that we have here, we can say that the mass deposited is proportional to the copper ions discharged. This is directly proportional to the number of electrons, hence the charge of the battery. So this charge that we're talking about is charge of battery. So let me say that one more time. The mass deposited is proportional to the number of copper ions discharged. This is directly proportional to the number of electrons, hence it's proportional to the charge of the battery. This is where we get this relationship from. Connecting this back to our Faraday's equation, this in general talks about the number of charge in general that you provide to this electrolysis setup. But here we're talking about the charge in 1 mole of electrons, which makes sense because we're looking at 1 mole and charge in 1 electron in our equation. So this is how all of this connects. So by knowing the moles of electrons, we can find the moles of the substance, and that leads us to the mass of the substance. So this chain is sort of how we derive or calculate the numbers that we need. So the moles of electrons can be written as total charge passed divided by the charge of 1 mole. So that will be the number of moles of electrons. And the total charge passed, if you are a physics student, you might know this, would be the amps times the time. Or you can write this as IT. Q equals IT, a very common equation. Therefore, we can say moles of electrons combining these two equations, IT divided by F. So where did this F come from? Now we know that Faraday's is the charge in 1 mole of electrons. So if we say this is F, total charge is Q, and the moles of electrons, as we know, is here. So all we did was replace this with F and this with IT. So we have a very useful equation here for our calculations. So the 3 calculations that you need, that they will probably ask you to calculate, is Avogadro's constant. This is a very common experiment done with this electrolysis because you know all of this information here, so you can just plug in and find L, which is Avogadro's constant. So a lot of the times in the exams they ask you to do that. And the second calculation would be the quantity of charge passed. And the third thing they can ask you is mass of substance liberated. So this can be a solid or a gas. If it's a gas, then we will look at the constant 24,000, which is the ideal gas constant. So this is 24,000 centimeters cubed for every mole of gas. So let's look at these 3 more in depth on how you will approach these calculations. Another 4th calculation that they can ask you is the time taken for X grams to be liberated. Now these 3 are basically using the same equations, but we will just have to rearrange a bit. But I will show you how to do these step by step as well, just to make it clear. So this will be the mass of the substance liberated, and they will give you a certain time, and this will just be time for certain X grams of mass to be liberated. So again, these are connected, but let's start off with the first one. So first, I will go step by step on what you need to do to calculate, and then we'll look at an example just to make things clear. So step 1 is to calculate the moles. So now we all know the common moles equation. So this is fairly straightforward. But one additional note that you need to take is that if the ion that we're looking at has a +2 or +3 charge, then you will need to multiply this by the number of electrons that that ion gains to make it into an atom so that mass is liberated. So to look at this, you need to look at the half equations. Now, this can be a little complicated, but as you practice, I swear it will get easier. But half equations are also given in your data booklet if you do CIE subjects. So if you have chemistry CIE, you will be provided with a data booklet, so you can just look at the half equations from there and it will make your life a whole lot easier. So if you have copper, for instance, then you have Cu2 plus 2E gives you Cu. So we want this ion to be transferred into a copper atom so that mass is liberated. So we need 2 electrons from this. So we need 2 moles of these 2 electrons. So what we have to do is multiply the number of moles by 2. But in general, I will just say number of electrons in half equation. So now this doesn't necessarily have to be the charge that the ion has, because if you look at O2 minus, this has -2 charge, but if you look at the half equation, this is a diatomic, so this will be 2E, which will give you an O. Sorry, this is not plus, this is minus. Or you can just put 4 plus on the side, because this is oxidized from an anion to a gaseous substance. So over here you have 4 electrons needed because this is a diatomic. So this will be multiplied by 4, not 2. So be careful to not just look at the charges, but also look at the half equation and the number of electrons required to make it into its pure substance. Step 2. This can be done with the equation that I gave earlier, Q equals IT. So in the question, they will generally give you the current that is applied to the battery and the time that it's applied for, so you can calculate the number of coulombs with this equation. Step 3. You will take the number of coulombs calculated from step 1 and divide that by 1.6 times 10 to the minus 19 to give us number of. So this will give you the number of electrons. Now step 4, we will just have to divide, for Avogadro's constant, we just have to divide the answer we got in step 3 divided by the answer we have in step 1. Because we have number of electrons divided by the moles that we have, which gives you the number of atoms in 1 mole, which is essentially Avogadro's constant. So number of electrons divided by the moles. And then we have RL, which is Avogadro's constant. Now let's move on to the second calculation, which is calculating the time taken for X grams of a substance to be liberated. So step 1 of this is to calculate the moles of electrons. So the moles of electrons, as you know by the mole equation, is mass over mR. And again, as we mentioned here, we have to apply the same rule with the multiplication of the number of electrons according to the half equation. So the step 1 remains the same as the first thing. So step 2 would be, so we know that Q equals IT. And to find Q, we can say it is F equals F multiplied by moles. So this equals L times E times moles. Now why can we say that Q equals F times moles? This is because F, as we mentioned earlier, so we know that this is charge on 1 mole of an electron. So charge on 1 mole of an electron times the mole of an electron gives the overall charge. So we can write this as this, and just re-equating this with this gives us the equation IT equals L times E times moles. And then we can just rearrange for time, so L times E times moles divided by the current gives us the time taken. So I would say to copy down this equation as well, as it's very important and very handy. This isn't really an official equation of anything, but this is very handy in doing long calculations like this and makes it a whole lot easier. So that's it. That was the two-step quick process. And number 3, we have the calculating the mass liberated. So step 1 would be to calculate the number of coulombs. And we can use the equation Q equals IT. IT will be given in the question usually. And step 2 would be to calculate the moles of electrons, which will be the coulombs divided by F, which is Faraday's constant. And this comes from this fact right here. This and this is basically the same because it is just moles times F equals Q. Again, moles times F equals Q. So, same thing. I hope you can see that. And then step 3, you need the moles of the ion. So this will be the moles of the electron divided by number of E in the half equation. You're like, whoa, where did this come up? Well, you could see here in this example, we calculated the moles of electron using mass over mR times moles of E in the equation, E as in electrons in the half equation. And this is moles of ion equals moles of electron divided by moles of electron in the half equation. So if you can see, this and this is basically the same thing. You are just rearranging it because you are just transforming this part to moles of ion. So you can write this as mass over mR. So as you can see, this times this will give you the moles of E. And then here again, this times this gives you moles of E. So this is the same equation, but we're just transforming it a bit. So step 4, the mass of the product is equal to moles of ion times mR. So this is again from the general moles equation, mass equals moles times mR. And the moles that we use is the moles of the anion calculated from step 3. So as you can see, these equations connect with each other, and I hope it's clear with how I've derived each equation and how I've used the steps. So this is the basic calculation that they will ask. And one last calculation that we haven't looked at is the quantity of the charge passed. So this is basically either Q equals IT, but if they make it a bit complicated, they might not give you IT, and they might make you calculated with using the mass and the time, or maybe the Avogadro's constant as well. It depends on what information they provide with to you, but I would just say two equations that you need to keep in mind is this and this. These are basically the only two equations that we have used thus far, but we have just transformed it in different ways. And if you are not really a mathematical person and you just like to memorize equations to get calculations done, then I would say memorize this equation as well. Even though it is straightforward because you're just dividing a large quantity with the quantity in 1, which gives you the number of items, as we learn in basic division. But I can understand that when coulombs and when constants come into play, this simple concept might become a little hazy. So I would say these three equations are all you need for these calculations. But if you are very confused still, then I would say just go through it step by step as I have told you here, and just look at what the question is asking for ultimately in the end. So there is all the calculations done. Now let's move on to some of the theory-based knowledge that you need to know for electrolysis. So let's start with electrode potentials. Now this is a new concept if you are starting off in A2. So electropotential is basically when metals react, they give away electrons to form positive ions. We know this. Metals form positive ions. So electropotential is basically comparing the ease with which a metal does this, so from which a metal goes to a positive ion, compared to a standard hydrogen ion. Now we have made this hydrogen a standard, I don't know why I put 2 plus. We have made hydrogen to be a standard, hence we say that the electrode potential is 0. And whatever metal we compare this hydrogen, this ease with how hydrogen goes from hydrogen to the hydrogen ion, is the electrode potential of that metal. So again, this is basically just comparing metals to hydrogens with the ease that they form their electrons in. And this can be done with an electrolysis process. If you have water and you put in a magnesium strip into this, the magnesium will basically react with the water, and I'm just drawing these holes to show the 2 plus that comes off to form the magnesium ion. So then this solution will become an aqueous solution with the magnesium ions, and these magnesium ions basically dissolve. So there will be a tendency for the magnesium atoms to shed electrons and go into the solution as magnesium ions to form this aqueous solution. And that tendency is measured by the electrical potential, the electrode potential. But over time, there will be a buildup of negative charge in the metal because of the positive charges in the solution, and these positive charges will be attracted back to the metal. So now when we have this to and fro motion, we basically form an equilibrium. So the equilibrium form will be Mg2 plus 2E minus, and this equilibrium sign to Mg solid. This is aqueous. So we form this equilibrium solution, and this equilibrium, if you see in your data booklet, is stated, and the electrode potential is written of this is basically minus 2.38. So this shows nothing but the magnesium ions going to form the magnesium atom. Over here I said that metals to a metal ion is electrode potential? Well, you can see here with the negative sign, since we're moving backwards from an ion to an atom, there's a negative sign here. But going from an atom to an ion, the electrode potential expected will be positive. So all this is comparing the tendency for magnesium to form its ion, or if we're looking at the opposite, the ion to form its atom, compared to the tendency of hydrogen ions to be formed from the hydrogen atom. So this is the standard, and this electrode potential comes off from comparing to the standard. And I hope that is clear. Now, the standard hydrogen electrode is what you need to know in your syllabus, and here is a good example of the standard hydrogen electrode. So you need to memorize this for your exam, how to draw this out and what to label things. So the standard hydrogen electrode, you basically have this tube and hydrogen of 1 bar. This is basically the pressure of the hydrogen gas that's entered in. So you write 1 bar or 1 PA, 1 Pascal. And you label the platinum wire, and you label the platinum foil covered in porous platinum. So this is basically acting as the electrode here. And the solution that it's diluted in is dilute sulfuric acid, and you need to make sure it's 1 mole decimeter cubed. So this whole setup is quite different from what you've learned in IGCSE, but there's a few things that you need to keep in mind. Oh, also the standard temperature is 298 kelvins. You make sure it's in kelvins, not in Celsius. So these are the things that you need to mention for drawing the standard hydrogen electrode. And how this differs from the standard electrode cell that you draw in IGCSE is that this has a high resistance voltmeter rather than a battery. And it also has a salt bridge to connect these two these two electrodes, rather than having 1 tank with 2 electrodes in the same solution. Now the reason why we do these 2 different different beakers, is because we require different solutions depending on what metal we are looking at. So this salt bridge basically helps connect these 2 and form 1 whole circuit, so the electrons can travel through the whole circuit. Now this is very important because we are using a high resistance voltmeter. Let's draw this out here. So how electrode potentials and a standard electrolysis battery differs, this has a negative and a positive plate. So whatever electrode you connect here will gain electrons, and this will become the cathode. But here there is no negative or positive plate. The electrons can go from this, electrons can flow like this, or they can also flow like this. This depends on the electrode potential that you're looking at. So if you have magnesium here and you have the standard hydrogen electrode here, I will just draw a rough sketch. We know the electrode potential here is negative, but the hydrogen is 0, 0 as it's a standard. So when it's a negative, then we know that it's being is negative. Then the electrode is being reduced. But if the electrode potential is positive, then the electrode is being oxidized. This is very important to know. And depending on what metal you attach here, and looking at whether the electrode potential is positive or negative, the electron flow will differ. So since in this case magnesium, the electrode potential is negative, then the electrons will have to come into magnesium so that it can be reduced. So the electron flow would be like this. This is the salt bed. Remember, this is connected. So the electron flow will be like this. I hope that is clear. So we can just cancel this out. So the electron potential is going from magnesium, coming out from the hydrogen, standard hydrogen electrode. So now another thing that you need to know is how do you draw this electrode potential, and how do you know what solutions that you're going to use? Well, there are three cases to know for electrodes. So if you have a metal going to a metal ion, the electrode that you use is the metal itself. If you are going from a metal ion to a metal ion, so for example, if you're going from Mg plus to Mg2 plus, so there are cases where past papers can ask this, then the electrode that you will use is an inert electrode because you don't want the metal atom to interfere with the ion transferring to an ion. The electrode that you will use will be platinum because it's inert. And another case is if you have gaseous elements to test, so any gaseous elements, the electrode again will be inert, so it has to be platinum. And as you can see for hydrogen, since hydrogen is the gas that you use, hydrogen gas is here, then the electrode that we used here was platinum, which was an inert electrode. Another thing to remember is if you do use a gaseous element to test with the standard electrode, then you need the tube as well. So tube is required to transfer the gas and make it react with the platinum electrode. This will be the gas, and remember the gas will have to be 298 temperature, 1 atm pressure, and the solution used will always be any H plus solution, so it could be sulfuric acid or any other acid, and the concentration will have to be 1 mole per decimeter cubed. So that is all you need to know about labeling the electrodes and drawing the electrodes. So this is the basic rules. So we have looked at how to predict the electron flow by looking at the signs of the electrode potentials. We've looked at the types of electrodes to use and how to draw and label our electrodes. So we will look at the feasibility of the reaction. How feasible is the reaction and will it take place or not? Now what we mean by feasible is if you look at the electron flow, we need to make sure that the electron flow actually occurs in one direction, because if the electron is going like this, since we know that there is not one singular circuit like a battery which will make sure the electron goes into one way, the electrons can go like this or like this if the reaction is, if the electrode potential allow it. So when we have these cases, the electron flow is not in one singular direction, then the reaction will not be feasible. So how do you calculate this? So to find out the feasibility, we need to calculate the total electrode potential, and the equation we use for this is E total equals E reduction minus E oxidation. So this is the electrode potential of the electrode that's being reduced and the electrode potential of the electrode that's being oxidized. So now if we go back to our magnesium and hydrogen example, the electrode being reduced is magnesium reduced. And the electrode being hybridized the electrode being oxidized is the hydrogen, so it's being oxidized. So the total electrode potential of this will be the electrode potential of this being reduced minus the electrode potential of what's being oxidized, which is 0. So the total electrode potential is minus 2.38. And this is why we compare it to the standard, which will remain 0, so we can find the electrode potential of the metal that we want. But obviously this is not the case for all our experiments. We don't always compare it to the hydrogen electrode. We might also compare it to another electrode, such as copper. So if we have our magnesium and our copper electrode, saying this is copper, this is magnesium. I won't draw the whole thing in detail, but just to give you an idea, the total electrode potential. So the magnesium is minus 2.38 as a standard electrode potential, and the electrode potential for copper, that is 0.24. So what's being reduced minus what is being oxidized, this will give us minus 2.72. Now how do I determine whether this is feasible or not? Well, if this total electrode potential is less than 0, then the reaction is not feasible. But if the total electrode potential is greater than 0, then the reaction is feasible. So that is the general rule that you need to remember. If the electrode potential is less than 0, then it's not feasible. If the electrode potential is greater than 0, then it is feasible. Now we only use this equation when we have standard conditions, and our standard conditions is temperature to be 298 kelvins, pressure to be 1 atmospheric pressure, and the solution to be 1 mole decimeter cubed concentration. When we don't have these conditions, then we use something called the Nernst equation. And the Nernst equation is basically, I hope I'm pronouncing that right, Nernst equation. I'm not entirely sure, but this is how I read it. This is basically the Nernst equation. The electrode potential that you start with. This is basically what's given in our data booklet. So if we're looking at magnesium, like magnesium plus going to Mg2 plus, then in your data booklet you will find the electrode potential of magnesium plus, and this is what you will sub into this term. And then Z is basically the difference in the charges of the ions. So this is the difference. You have a +1 difference in the charges of the ions. If you're going from an atom to an ion, so if this was magnesium to 2 plus, then the difference would be 2 plus in their charges. So Z is that difference. And then it's the concentration of the oxidized substance divided by the concentration of the reduced substance. So if you're going from a +1 charge to a +2 charge, it is being oxidized. So the oxidized substance would be Mg2 plus. So the concentration of Mg2 plus will go here, and the concentration of Mg plus will go here because it's being reduced. And that will give you the total electrode potential in non-standard conditions. So if you have standard conditions, you can straight away go to this equation, but if you have non-standard conditions, you will have to use the Nernst equation. And if you do have standard conditions and you put it into the Nernst equation, it should work either way. Now the last thing that you need to know for electrochemistry is when you change the concentration, what happens to the electrode potential? Does it increase or does it decrease? Well, for this, all you need to do is apply Le Chatelier's principle, and this is what you've learned in IGCSE. So let's look at an example. If you have this equation of zinc, so this is an equilibrium equation, and the electrode potential for zinc is minus 0.76. So if the concentration of Zn2 plus increases, then the concentration of Zn would have to increase to compensate for the increased concentration of Zn2 plus, and so the forward reaction will be favored, and so the electrode potential will become more negative. And then if the concentration of Zn2 plus decreases, then the backward reaction will be favored, and so the electrode potential will become more positive because the forward reaction is more negative, so the backward reaction will cause it to be more positive. And that is basically a general rule that you have to apply. Quite simple, nothing too complicated about this. And yeah, that is basically all of electrochemistry covered for A2, all of the basic concepts and the basic ideas. In the future, I will potentially look at any new past paper questions, any complicated questions that you want me to look at, but these are the basic concept of A2 electrochemistry. I hope this video was helpful for you and I hope you enjoyed. Please do leave me a comment for any topics that you want me to cover first, but I will be covering the entire syllabus one by one for chemistry, physics, and for the maths for A2. Bye-bye.